Hello, in this presentation I will show you how to determine which relations are functions and how to represent them as rules, tables, and graphs. A function is a specific relationship between the input and output. For each input there is exactly one output. If you look in this table you can see that all the inputs are different. The domain is the set of all input values in a function. We call this the independent variable, and usually it is x. The range is the set of all output values in the function. The range is the dependent variable, usually the y. When we're going to list these domains and ranges, make sure that you list them in increasing order without repetition. For example, to list the domain of the table over here, we're just going to write the numbers 1, 2, 3, and 4. Notice that we use the braces to group the numbers. For the range, well, since we have to go from least to greatest, -19 is the smallest number. To help you with functions, I want you to think about this example. Where do students belong at the beginning of 4th period? If you look at the first schedule over here, we can see that Adam's name comes up twice, and he is told to go to 2 different classrooms. This is not possible because he can't be in 2 locations at the same time. In the next schedule, we see that Crystal's name repeats twice. However, in both situations, she's going to the same room. This is possible because the room is just repeated twice. In the last situation, we have all different students going to the same classroom, FX 221. This is also possible. You can have many different people in the same classroom. Now I want you to think about that example as we do the following problems. So we're going to write, does the table represent a function, and explain. A quick hint is to circle any repeating inputs. If you look at the first example, the input 5 repeats twice. This is very similar to the previous example where Adam repeated twice. In this situation, this is not a function because the input 5 has 2 different outputs. In the next situation, the input 2 repeats. However, the output is the same. So really we're just talking about the same point and being redundant about it. This is a function, the input 2 repeats, but the outputs are the same. Finally, in the last example, we have all different inputs and the same output. This is a function, all inputs are different. You could also just give the definition of a function as a reason. Each input has its own output. Here are a few examples where we will identify the domain and range of each relation. In the first relation, we have a mapping diagram, and it shows the input 4 goes to the output -1. The input 5, if you follow this arrow, goes to the output 23. I would recommend you make a table for a better visual, and you will need 1 row in the table for each arrow. So pause the video here and go ahead and make the table. Here is the table. As you notice, the input 4 and the output -1 would be represented by that arrow. If you count all the arrows, we have 1, 2, 3, 4, 5 arrows, and 1, 2, 3, 4, 5 rows. Remember, when you list a domain and range, you're going to go in increasing order without repetition. So the domain here is going to end up being 4, 5, 7. Our range is -1, 12, 20.8, and 23. If you were asked if this was a function, we could conclude that it's not a function, and for that reason, this table shows you much better that this is not a function. In the next example, we would have a domain of -2, -1, 0, 1, and 2. That's fairly easy. And for the range, you might have to be careful here. The lowest range is 4. So let's cross it out and write the range of 4. Then next we have 2 5s, but we're only going to write them once. Next we have 8. And finally 13. And there's the range. 4, 5, 8, 13. In the final example, we have a bunch of ordered pairs listed as x and y. X is the input, y is the output. For the domain, start with lowest, go to greatest. The smallest x value we have is -5. Next, I see 2 -2s. And 4 is remaining. And the range, the smallest range I see is 5, but we only write it once. And then we have 6, and finally 12. So the range is 5, 6, and 12. It's important to note that none of these relations here were functions because each input did not have its own output. Let's make an input-output table for the function y equals 3x plus 2.5. We're going to use 0, 1, 2, and 6.3 as the domain. Then we're going to identify the range. Once you make your table, label it as input. I usually leave a column for the work so that the output can be clearly visualized. Let's list the inputs in order. Here they are. And when we write in the work, very important that you put these parentheses around there. So if you write out 3x plus 2.5 with parentheses, it's much easier to substitute that 0. 3 times 0 gives you 0 plus 2.5, we get 2.5. We repeat the same thing for the next one. We get 5.5. 3 times 2 is 6, plus 2.5 is 8.5. And the last one, we get 21.4. Take your time when you do the math and check it with a calculator. All of these outputs, the y's, are the range. And luckily for us, they're in increasing order, so we have a range of 2.5, 5.5, 8.5, and 21.4. A vertical line test can be used to determine if a graph is a function. A relation represented by graph is a function if an imaginary vertical line passes through the graph at 1 or 0 locations. In the first example, we have a graph represented by this red line, and if we make an imaginary vertical line, and we use a dashed line to show that it's not part of the graph, we see that it only hits the graph once. Therefore, that graph is a function. In the next example, the vertical line doesn't hit the graph, and here it hits it only once. For that reason, that graph is also a function. If an imaginary vertical line hits a graph 2 or more times at any location, then the relation fails the vertical line test. As a result, the relation is not a function. In the first graph, we see that that imaginary vertical line hits the graph twice. And in the next graph, we hit the graph 3 times. Therefore, both this graph here and the graph here are not functions. Example, determine if the graph is a function. Explain your reasoning. Well, this first one, since it's a graph, we can use the vertical line test. Here, the graph isn't hit, so it passes it. Here, it hits it once. It's still passing the vertical line test. However, here, the graph is hit twice, and therefore it is not a function because the graph fails the vertical line test. Next example, we have a scatter plot, and you can see at that location there, the graph is not a function because it fails the vertical line test. And finally, we have a step function, and it passes the vertical line test, and it even passes the vertical line test here because the graph is hit at that location, but there is no point here because there's an open circle. As a result, the graph is a function because it passes the vertical line test. Just a little bit more information about the greatest integer function, aka the floor function. Here are the ways you can express it. And the rule just says that you're going to round the number down to the closest integer. Floor 1.7 is 1. Floor of 83 would be 83. If you have a negative 3.51, the greatest integer is negative 4. And 5.999, the greatest integer function was 5. Even though it was close to 6, the answer is still 5. Is the graph relation a function? Explained with two different reasons. Well, since it's a graph, we can use the vertical line test, and we could see that it is not a function because it fails the vertical line test. And we could also take 2 points from the graph and write their ordered pairs, and we could see that the x value 3 has 2 different outputs, therefore it is not a function. If we were to identify the domain and range, we have a continuous domain in this graph, and you can see the domain stretches all the way from when the x is negative 8 to when the x is 7. So we write that domain as a compound inequality. So the domain is negative 8 is less than or equal to x, which is less than or equal to 7. Similarly, the range, the lowest range is negative 3, and the highest range here is at 9. So we write the range as a compound inequality as well. Sometimes relations can be represented by an equation, and as you can see here, we have an input and an output, which we're going to use x and y to represent each one just to make our equation easier to write. And if you look at the pattern between the inputs and the outputs, you will see that to get from 10 to negative 50, we can multiply the negative 5. Therefore, our equation is y equals negative 5 times x, or just negative 5x. If you're asked to write a verbal rule, just say the output is equal to negative 5 times the input. Here's an example. It's a little bit more difficult. We have a few x values, a couple here in a row, 4, 5, 6, and y values that are larger and increasing. I'm going to just try something. Because I see 2 and 20, and I know that 2 times 10 is 20, let's try. Maybe that's the rule. It is true for the first scenario. However, 4 times 10 is 40, and we need this 40 to be a 42. So we know that's not the rule. If we look at the y value, we could see that each time the y is being added by 11. And maybe we should look to multiply by 11. I know that if I said 2 times 11, that would be 22. So subtracting 2 will bring us down to 20. If we try another one, 4 times 11 is 44. Minus 2 gives us 42. And that 42 matches this 42. We can confidently say that the equation is y equals 11x minus 2. The verbal rule is that the output is 2 less than 11 times the input. Let's do a few extra examples just to summarize what we've done. Is this graph relation a function? Explain. Well, it passes the vertical line test here because it doesn't hit the graph. And the vertical line hits the graph only once there and once there as well. Therefore, the graph is a function because it passes the vertical line test. Identify the domain and range of that graph. Well, the graph begins at this point here, and the x's are increasing while the y's are decreasing. Because it's an open circle here, we can't have the value -2 as an x value, but we can have the next number larger. Therefore, the domain is x is greater than -2. The range, y is less than 7, because y is always going to be less than 7. As you see, the graph keeps going down. Example, express the relation below as a mapping diagram, a graph, and a table. We have a bunch of ordered pairs, 1, 1, all the way to 3, 4. Let's first make a mapping diagram. We're going to list all the inputs from least to greatest, all the outputs from least to greatest. You can see the outputs, we have -1, -1 here, and so forth. Just take your time to do this correctly. And now we just have to map it. So 1 goes to 1, make an arrow. -4 goes to -1, and continue to all the rest. To make a graph, we need to make a coordinate plane. Here it is, and we need to graph the point 1, 1. Always make sure you start at the origin at 0, 0, and 1, 1 means 1 to the right and 1 up. So we make a point there. -4, -1. Go to the origin, left 4, bounce 4 times left, and then 1 down, and do the same for all the other ones. And finally, table is probably the easiest. Just make sure you label it and write each ordered pair next to each other. If we were asked, is this a function? What do you think? It is not a function because, one, it fails the vertical line test, which you would see over here, and the input 1 has 2 different outputs. Next, I'm going to talk to you about function notation. It's a way to write an equation so that the input is clearly specified. It's more common in higher level mathematics, and you will see it on the SAT and ACT. f of x equals -7x plus 1 is similar to writing y equals -7x plus 1, and you can read the f of x also as the value of f at x. Quick caution, f of x does not mean f multiplied by x. Okay, this is the only case where two variables next to each other does not mean multiplication. Let me show you a quick example. Evaluate f of x equals -5x minus 13 when x equals 2. So we start by substituting 2 anywhere you see x. So we had an x here and an x here. We substitute with parentheses. And now just simplify. This f of 2 is like a y. So just keep writing it as f of 2. 5 times 2 is 10, minus 13 gives us -3. And that's it. There's nothing else to do here. That is our answer. The way you would read this is f of 2 is -3. The advantage is that you can see that the input was 2 and that the output is -3. So both are conveniently packaged in that one line. And here's just a few things of how we can express independent variables and dependent variables. Just take a look at that, refer to it later. Make an input-output table for the function f of x equals -7x plus 1 with that domain. Then we're going to sketch the relation. So let's just make our input-output table. I'm going to have room for the work over here in the middle, and the output we will call f of x. So just write all the inputs, and when you substitute, just take the right side of the equation, this part over here. Anywhere I see an x, I'm going to use parentheses and substitute to -2. Show your work, and you will get your values. 0 is usually the easiest one. Gives you the constant, which is 1 over here. When you multiply fractions, you might need to do the scratch work somewhere on the side of the notebook. You know, -7 over 1 times 3/4 gives you -21 over 4 plus 1 is going to give us our final answer of -4 and 1/4. and confirm it with the calculator as well. And when you substitute 5.1, we get negative 34.7. Since we're only sketching the graph, we don't need to have a scale. We can just estimate where negative 215 would be. So I know negative 215, you would start from the origin, you go a little bit to the left and somewhat up. So just estimate it as best as you can. I'll make the y steps, scale a little bit larger. And those would be our 4 points. Here we will apply function notation to a word problem. We have a pizzeria charges $9 for a large cheese pizza and $1.50 for each additional topping. Identify the independent and dependent variables. Write an equation in function notation. So we need both of those. It might be easier to write the first sentence, with the word depends. And since you pick the toppings, the total price for a large pizza depends on the number of toppings. And therefore, the total price is the dependent variable. Therefore, the number of toppings is the independent variable. To write the equation, we're going to take the independent variable and define it. So I'm going to let t represent the number of pizza toppings. And since I'm paying $9 no matter what, the number of toppings is going to get multiplied by 150. Therefore my equation is f of t equals 9 plus $1.50t. And you might even see the equation that way, but I actually prefer this way because it shows you that you're paying the $9 out front and then the toppings are going to get added on top of it. Thank you for watching.